Thank you very much, Hans, for the kind introduction. First, good morning, good evening, good afternoon, wherever you are. I'm quite impressed by the attendance, so thanks for being here. Thanks also to the organizers of the Electrification Academy for inviting me to talk about the comparison of electricity generation options, coming mostly from a report that was published this year with the United Nations Economic Commission for Europe. So for the next 30 minutes or so, we will go through the main findings of that report with a few updates here and there to make it more topical, let's say. I will start to introduce myself very quickly. So my name is Thomas Gibon. I have an engineering background from France, and I have a PhD in something called industrial ecology from Norway. I now work at the Luxembourg Institute of Science and Technology, or LIST, which is the main research and technology organization in Luxembourg. The main for a small country, but we're quite active in this kind of topics. Very happy to be here. And now let's get started. So I will start with something quite important, I think, for the rest of the presentation, which will be some notions about lifecycle assessment. Lifecycle assessment is a tool that we use to first account for all emissions, waste, and also inputs of energy material that are linked directly or indirectly to a final demand for a given system. So I will explain to you why we do this. So the first thing we have to keep in mind is that human activity pressure on the environment is skyrocketing, right? So we have to keep monitoring all these impacts, be it emissions of CO2 in the atmosphere, which is probably the most famous environmental impact these days. But there's also a few other things that we emit in the atmosphere, such as N2O, methane, and there's other pressure, other types of pressure on the environment that we cause through human activities. So on the one hand, we need to produce and to support decision making with complete, accurate information about the environmental impacts of what we use. What we use can be anything from products, technologies, organizations, even lifestyles. If you know about individual carbon footprint, then the understanding behind it is life cycle thinking, and that's an assessment of your lifestyle. And on the other hand, we also need to ensure a safe, affordable, and fulfilling future, right? We could obviously reduce environmental impacts if everyone was living in 10 square meters and eating on only soybeans or bread and water. But that's not really what we want. So we want to find this balance between, on the one hand, limiting environmental impacts and not crossing the so-called planetary boundaries, and on the other hand, satisfying, finding a satisfying life for most of people. And for that, we have to use energy, a certain amount of energy. So there are some scenarios. For example, this is from the IPCC 1.5 degree report, which was published a few years ago now, trying to assess how much final energy we would need to be able to sustain our lifestyles by 2050 and 2100. These different scenarios actually range from very low to very high value, depending on a lot of assumptions in terms of demand. Which means that we need to make efforts to be able to produce that energy. We know that to decarbonize our economy, one of the main solutions is to electrify it. And the most ambitious scenarios in the IPCC assume that by 2100, I think, yes, 60% of the economy will be electrified from about 20% today. So that's a huge leap to pretty much an electrify everything economy. In which case, we also have to decrease the carbon content of electricity. So on the one hand, we need more electricity. The overall energy demand will keep increasing because more people need to increase their energy demand than people that need to reduce it. And that energy will mostly be electricity, and that electricity will mostly be low carbon. So that's a few challenges we need to address. At the same time, carbon is not everything, right? We need to make sure that we don't increase other environmental impacts, which I call here environmental costs, but it's not monetary cost. Of course, you could lead to monetary costs, but first, what is the increase in land use? What could be the increase or decrease or other kind of topics or issues related to materials, and what could be other issues in terms of water stress, toxicity, particulate matter emissions, air quality, etc. So how do we assess our options? You may have seen in the press, usually that kind of announces. So that paper cup is actually better or worse than an actual cup, cotton totes, biofuels, solar power, nuclear power. All these claims, normally, they're well made, should rely on life cycle assessment. So we need this life cycle approach, which means, let's take the example of electric cars. These cars have almost no emissions during the use phase, maybe a little bit of particles, but that's not so much. But most of the emissions will actually happen upstream of the system, either because you need to make a car or you need to manufacture a battery, or because you need to produce electricity. And all impacts don't happen under your eyes as it does with a diesel car, but you still need to account that if you do a life cycle assessment. Fortunately, at least in Europe, there are regulations and directives that recommend life cycle assessment. Even in the US, the California Low Carbon Fuel Standard recommends that cars' performance be used or be assessed with life cycle assessment. The EU Directive on Energy-Related Products, for example, is using it. The Waste Framework Directive is using it. And perhaps most famously lately, the EU Taxonomy is using a life cycle approach to determine which investments could be deemed green and which not for the energy transition in Europe. So now let's dive a bit deeper into the definition of what life cycle assessment is. First, what we could say is that it's a method and a tool for attributing environmental impacts to products and services. We have to consider the impacts over the life cycle of the product, not only the use phase, obviously. The product actually has a whole supply chain upstream, and also we need to take into account the impacts of discarding and treating the waste for this product. So we call it holistic. It's a holistic approach because we take into account everything. And at the same time, we also have to consider hundreds of emitted substances and extracted resources. So that's a bit of the difficulty in life cycle assessment, because that typically covers hundreds, if not thousands, of substances, from greenhouse gases, which are, I think, about 100 in the databases we use, to toxic compounds, which could be thousands, to land or water indicators as well. So that's a lot of criteria we want to assess and to take into our modeling. So it is a multi-criteria method as well. So these are the two main important points. Holistic is important because you don't want to forget that you will emit CO2 somewhere, maybe in a blind spot of the system that you haven't considered. And multi-criteria because you don't want to find out later that you would actually have higher impacts that is not CO2, but for example, you could have higher material or land requirements than conventional alternatives. So it's really important to identify co-benefits and trade-offs of decarbonization. A quick example with wind power. Typically, you will start by accounting the amount of raw materials you need to extract together with the energy inputs, with the infrastructure and the land use for the extraction of these raw materials. Of course, it depends a lot on the assumptions you made in terms of recycled content in your products, but there's always a little bit of virgin material in most of the products you assess. Then you will have to produce the different parts for a wind turbine. So that takes into account the transformation of iron ore into steel, but also all the copper that goes with it. Again, depends on the assumptions on recycled content. There's a lot of transportation between, actually between all the spaces, not only there. And at the end, you will have, for example, the construction. For offshore wind, it's quite important to take into account the back and forth of the different ships, which actually appears a little bit in the life cycle environmental profile. Operation maintenance of this equipment is, of course, taken into account. For renewables, it's not that much. It's probably changing one or two parts once in a while, and all the maintenance trips that operators have to do. And end-of-life management, which will also take into account some sort of treatment. Of course, we try not to double count both the use of recycled content at the beginning and the recycling at the end. So there are different approaches to do this. Either we take one and not the other, or the other and not the one. So that's that there are different approaches to LCA, but this is not the topic for today. And of course, the exchanges with the biosphere. So along this process, we will actually take stock of all the emissions, literally thousands of emissions. We don't do that manually. We have databases to do it, but in the end, it happens to be about 1,000, 2,000, maybe 3,000 substances that we translate that into indicators. CO2 equivalent is not a substance. It's an indicator for global warming potential, which translates the effect of greenhouse effects on, in terms of radiative forcing, in terms of global warming in general. And you could also count the other way around, all the resources you take from the biosphere. What we like to do is that we do this for climate change. We can do it for air pollution. So this is recommendations from the European Commission Joint Research Center. You could see that there's a robustness column here where we actually don't consider all indicators with the same degree of robustness. There's always a lot of uncertainty because some of these indicators are really either local or, you know, have substances that could end up in many compartments. So it really depends where you emit them, where they can end up, etc. So air pollution, toxicity, radiation, eutrophication, and resources. These are the main ones recommended right now. Of course, there's other methods that you could use to assess technologies and products, but these are the main ones. So the ones with the one are the ones considered the most robust, of course, because CO2, for example, are greenhouse gases. We know how they work. We know the effect of it. It's a global problem. So if I emit 1 kilogram of CO2 where I am, or if we emit 1 kilogram of CO2 where you are, it's going to have the same effect, which is not true for all of those, which is not true for particulate matter, for example. Because if you emit particulate matter in a place when there's no one, it will have a much lower effect than if you do it in the center of a city. Okay, so the results we will show now are actually an excerpt from this report, Lifecycle Assessment of Electricity Generation Options, that we started almost 2 years ago now, and that was released earlier this year. It's part of a larger package called the UNECE Carbon Neutrality Toolkit, where you could also find some briefs on hydrogen, nuclear power, CCS, and other topics like that. So what did we find in this report? Yeah, first I should also say it's an update of an earlier report from the UN Environmental Program, where we were missing a few technologies. For example, nuclear was not covered in this one, so we collected data and we actually reproduced, or we did lifecycle assessment for this one, and we updated some numbers for the other technologies. So let's start with what we found for climate impacts. First, life cycle greenhouse gas emissions. I have to also say that we have a multi-regional model, but the data was regionalized in different ways for the different systems. So unfortunately, it's not directly comparable, but most of the background is regionalized. So for example, if we start here with hard coal and natural gas, the variation you can see in terms of grams CO2 equivalent per kilowatt hour here depends on the supply chains for coal and natural gas. So natural gas also takes into account emissions upstream of methane, for example, which is not at the same level if you extract it in Norway or in Russia. So this is normally taken into account in here. So the fossil sources obviously have some emissions, direct and indirect. So coal is mostly, traditional coal is mostly around 1,000 grams per kilowatt hour. Natural gas around 500. If you add carbon capture and storage, then you could decrease these emissions, but unfortunately this capture only happens at a point of emission. So you're not able to capture the CO2 emitted over the full life cycle, let alone the methane emitted over the full life cycle. And the capture rate is also not 100%. So that's why you still have some emissions left. And with a lot of difficulty, maybe natural gas recombined cycle would probably get under this 100-gram threshold that is planned by the EU taxonomy, but it's not guaranteed. So it's a bit of an issue with carbon capture and storage is that it doesn't make your technology zero carbon. It's a drastic reduction in emissions, but still emitting some CO2 and methane. And the other issue that we'll see after is that you might also find a problem shifting with other impacts. Hydropower, we had modeled two dams. Some were, let's say, a high and a low assumptions, hydropower dams, just to have some kind of variation. The nuclear power plant we modeled was the average nuclear power plant today around the world. We were, our findings indicate somewhere between 5 and 7, to be broad, grams of CO2 per kWh. Concentrated solar power, this one is quite variable because now we start looking into the renewables. So they're heavily dependent on weather and, for example, solar irradiation and wind regimes. So that's why you have some variation. For photovoltaics, it stays very low. In some regions, you could get to 20 grams of CO2 equivalent per kWh. Even better with thin film technologies. The reason is that making silicon is actually quite energy intensive. So you would need to emit a bit of CO2 to produce the silicon you find in wafers and and PV panels, but not with thin film, which is good news. Wind power, finally, with some variation between onshore and offshore. For some reason I gave before, there's a bit of maintenance that is additional for the offshore, which is not that much for onshore, despite a bigger load factor for offshore wind turbines. Offshore wind turbines can reach load factors of about 40. The best, I think, are doing 50%. And onshore is probably between 25 and 30%. So anyway, the good news is that all renewables are low carbon. And fossil fuels with CCS are barely there with our assumptions. The variations occur mostly in the background for the fossils and mostly in the foreground. So that will be load factors depending on the sun and wind. For the renewables. In terms of land use, that was an interesting one, where we saw that, for example, fossil fuels, especially coal, still had some land use, as most of the mines worldwide are still open pit. Of course, it's a mix between open pit and underground, so depending on the region, you might have something that's higher or lower, depending on how you source your coal. Natural gas doesn't really induce any land use because most of it is obviously underground, so we don't really account for it in terms of land use. It's higher for carbon capture and storage for something that, because of something we call the energy penalty. It's the fact that you will actually need more feedstock to run the capture equipment and all the subsequent sequestration, transportation behind it. So you need about 15% more energy to run the whole process, which means that for anything else than CO2, you will have a 15% more increase in terms of impact. For hydro, again, it's very local. This is very site-specific. It's hard to give a global average. You can give a global average, but it will have a high standard deviation, let's say. Nuclear is very low. The mix of mines right now is about 50% of in situ leaching, which is underground. It's fracking, but for uranium, so it doesn't take any space on the surface. And another quarter, I think, in underground. So the remaining open pit mines are quite minor, and since uranium is very dense energetically, you don't really see it appearing in this graph. And then you have all the renewables. For concentrated solar power, I want to be clear here. The regions for which we assessed, we found the highest numbers here are probably regions where there's never going to be any concentrated solar power. For example, in Japan, because the sun is so low there that it's not even economically feasible to open one there. So we have it for consistency, but at the same time, we should look at this range instead for concentrated solar power. And then you have variations in PV, depending if it's mounted on roofs or ground. And for wind, we have something really low, but I will explain why it's really low. It's because we accounted only for the surface of the masts, so of the towers. If you account for the full project area, you can be somewhere, at least anywhere between that range. So it really depends whether you take into account only the green dots or the full area around it. These are two metrics that you can use. It has different usages. Actually, it's been quite well detailed in this article by Our Data with whom we collaborated. You may know this website, but it's quite well done there. There's a full narrative why we found these results, and then they make this comparison at the bottom. I don't know if it's really clear on the screen, but for onshore wind, for example, it could be anywhere between 8 square meter per megawatt hour, or and 100 square meter, depending what you take in terms of land use. So first it's what you take into account, but also there's some potential combination with other uses. Roof-mounted PV is actually combined with the use of a building. Ground-mounted can be combined with agriculture for agrivoltaics, and usually it's not uncommon to find crops between wind towers, at least the onshore wind turbines, of course. So it really depends what you find as land use. And just to finish on that, the French TSO RTE, so the operator of the French grid, issued a report last year that go even deeper into the distinction between shared use, sealed area, and artificialized area. And of course, depending on what you take into account, land use can be very low or very high. So it really depends what you want at the end. I think this is a good case that illustrates that LCA is quite complex and requires good communication to really be able to interpret results properly. And they even go further, and we don't have to spend too much time here, but basically to compare the artificialization of the new energy system with whatever is going to be built in terms of roads, buildings, and any kind of other human-built infrastructure, to really put things into perspective and show, well, in the end, okay, it's a lot of land use, but it's really not much compared to our land use otherwise, which is highways, parking lots, anything else that it's orders of magnitudes higher. Now we can go to water. Water is not so surprising. Thermal technologies use water to cool their circuits. So you find the same, more or less the same pattern as before, with fossils being somewhere in the middle, fossils versus CCS being high. Now we see nuclear power coming up again because, of course, it's a thermal technology. And depending what we assume for at least the upstream, I think for silicon, you need a bit of water, but also for the maintenance, we have a bit of water to clean, panels and things like that. That's taken into account here. But overall, quite low. And hydro is low, surprisingly, but it's because the water that's returned to the environment is not assessed here. It's only water that's taken out of the environment. So either evaporated or used in the product or whatever. Now we can get to materials. So for materials, again, I have to give a caveat that this is a material footprint. It's not the amount of material in your bill of materials for the infrastructure. You won't find, so if you multiply these numbers by the amount of megawatt hour that will be produced over the lifetime of an equipment, you will find something much higher than the actual weight of the equipment. But it's because of the LCA methodology that has, that you need inputs of some material that not necessarily end up in a finished product. And we took the same list of materials as was given in this publication by the IEA from last year, just to have a point of comparison. So again, something a bit, usual by now, the fact that we have something medium for fossils, a bit higher for fossils with CCS. For hydro, it can vary quite much. And I didn't put concrete here, but if I put concrete, it would be much, much higher. Nuclear stays quite low, again, because of the high density of uranium and the fact that a nuclear power plant can produce a lot of power we took 60 years as an average for the lifetime. I know this was criticized since most of the nuclear power plants right now haven't reached 60 years, but the ones we're building are planned for 60 years. But of course you can change that, and there's a little bit of variation, maybe 10% variation on that number if you change the lifetime. And then with the renewables, it's a bit of a different story, especially for aluminium and copper for photovoltaics. Aluminium for the balance of system, which is everything else but not the panels or the modules. So that's the support, either on the ground or on the roof. You need about the same amount of aluminium per megawatt hour. Copper, you need some more connections. I have to admit, I forgot why for the root mounted, but it's a technology that requires the most copper per megawatt hour. And then wind will be a bit lower than that. So now if we look at these materials, I said we would compare. So this is what the IEA gives us for the same list of materials: copper, lithium, nickel, manganese, etc. So they do it for a car on top here, but they do it for power generation on the bottom. So I didn't do the direct comparison because they do it by installed capacity. So you have to translate that with the amount of hours that run, the amount of hours that a plant will run in its lifetime. Here they find that offshore wind and onshore wind actually have a higher material footprint or material requirements than solar PV because they count, I think this is still copper. They found that offshore wind has more copper. Probably there's some connection that we left out in the modeling, or we took into account that it was part of the grid. So again, another limit of LCA is that you need to know exactly what the scope is. Yeah, and the other one, I think it's zinc here. Yeah, so these are what we would call critical materials for the energy transition. But of course, you have other materials such as typically iron, concrete, aluminum, copper, which is more. Well, actually, you have copper and then this one. No, you have only copper, sorry. But here you have mostly what we would call bulk materials, which are also of concern if you want to upscale, your renewable grid. So it's not really an issue, but you have to be careful and to remember what the orders of magnitudes are here. So right now, this is just a comparison between different technologies, again, from another publication. You have hydropower on top. I think you can zoom, perfect. Hydropower on top here. So hydro will use a lot of concrete. Then you have some geothermal. Wind would use a bit of concrete as well for the base of the towers. And then solar at the bottom. But then comes aluminium. Again, that's something we found in our study. So this is consistent. PV is the main consumer of aluminium, and then all technologies consume copper for the connections. PV first, and then wind offshore. Sorry, first, and then onshore. So this is, I think this was quite a nice publication. There's another nice graph in there, which maybe we don't spend too much time on it, but shows that if we decarbonize, we might actually shift pressure from fossil fuels to materials. So this is the fuel intensity per country of the electric grid, and this is the material stock intensity of all these countries, also per unit of electricity. And you have obviously all the hydro countries here, because concrete is by far the main material we use in the electricity system. And then somewhere in between, you have mixes of renewables. You have France here with nuclear. And here you have most fossil countries. So it's really a switch we see from fuel intensity to material stock intensity. Again, it's not representative of the actual stress of criticality because, okay, we need a lot of concrete, but is that a problem? I don't know. So there is, again, another publication, and then I stop with materials, promise, that shows the environmental, social, and governance dimensions associated with different materials. So I also put this in the UNECE report. And that's also together with other indicators that indicate the volume or the future volume of each of these materials that could be needed for the future energy transition. I won't go too much into it. We can go through the questions later. Something I wanted to show, but that you shouldn't really take into account, and I will explain why, is that we can give a single score in LCA. There's not an absolute consensus on how we do this, but there's a way to normalize and weight the different impact categories that I showed at the beginning. We give them a score. For each technology, we just aggregate everything. And of course, there's a bit of subjectivity in there. So that's why we don't really like to show it, but also because it's in the report, I wanted to mention that, okay, we have single score indications, but of course, it doesn't really tell you whether it's an issue to replace CO2 emissions by particulate matter emissions, or this is very, this is subject to a lot of interpretation. We can go quickly through where impacts come from now per technology, but at daunting, it's going to be too necessary. I think it's quite obvious. For PV panels, it's mostly silicon production in blue here that dominates most of the environmental impacts. There's a bit of construction here, calcination effect because of the fuel used during the construction phase, and the inverters, and finally cell manufacturing will require most minerals and metals. But otherwise, it's, of course, everything is in infrastructure. For wind power, we have about the same with here foundation, tower, generator. So most of it is just the infrastructure of the equipment, not much else. And even blades here in blue are quite small in terms of contribution. And for nuclear power, it's mostly the upstream, chain of the uranium, from mining to enrichment to fuel fabrication, construction of the power plants, and a little bit of spent fuel management with, the storage, waste storage, and a bit of treatment as well. Okay. So I think one big conclusion is that all electricity sources have an impact. There's no free lunch. The question is just how much. So in terms of greenhouse gas emissions, of course, they're really low for all renewables and for nuclear power. For renewables, most emissions are embodied in the infrastructure. So it's also benefic in the sense that the cleaner the economy, the cleaner the power. If you manufacture photovoltaic panels in an economy that runs itself on renewables, then your photovoltaic panels will have a lower impact than if they were fabricated with coal power, for example, right? So there's this kind of virtuous effect, virtuous cycle that starts to appear in decarbonizing economies. That's quite nice to observe. We see also nuclear power as an environmental profile that shows low impact on all indicators. That's mostly because uranium is very dense. Of course, it doesn't take into account any other indicator that could be linked to nuclear power. But I don't think we have to talk about it here. LCA doesn't cover everything. Land occupation can be a concern, but it depends really what you account for. If it's plant or park level, or if it's sealed versus occupied lands, it's a bit of a tricky indicator to deal with. If you just look at project space, then you will need to take into account the space of a full wind farm, for example. But if you only care about how much space will be displaced from another use, then you will only use the wind tower land use, and then you will put sheep, or you will put crops next to it. Material requirements may be a concern, but of course there's a lot of uncertainty. It could increase significantly with high renewable scenarios. And specialty materials in general, specialty materials in particular, could be at supply risks. But again, there's a lot of possibilities, maybe of substitutability, or there are, maybe underestimated reserves that we haven't identified yet because we haven't used such or such material yet. And in life cycle assessment, it's quite difficult to assess for that. And to finish, of course, you can scale everything up. So now we talked about 1 kWh, but what happens with different scenarios we have for the future? So here we tried different scenarios, 4 scenarios. It's from a paper that was published a few years back, where we actually give different instructions. So 4 sets of instructions to 5 models, and they give us all very different future electricity mixes, which is quite interesting to observe that even with the same set of instructions, some models will be very solar prone, some will be very wind prone. But anyway, and then we applied our life cycle assessment factors to it. So what happens? For all our human health impacts, this business as usual scenario has obviously the highest impact because that's where you keep going with fossil plants. So this is everything but CO2, by the way. So you still have particulate matter, human toxicity impacts. And here you have a scenario with all technologies available, only conventional technologies available, and only new renewables. This is the one with the lowest health impacts. In terms of ecosystems, it's the same. Land occupation, natural land transformation come mostly from biomass. And then minerals and fossils in terms of resources. And then you can see that compared to our business as usual scenario in black here, most of the impacts are actually decreasing with the different alternative scenarios, except natural land transformation. I think, natural land transformation, land occupation, and mineral resource depletion. So that really shows where the next potential hotspots could be with decarbonization. Yeah, and then just to invite you to go look somewhere else, I already mentioned that, but the report numbers were used in this nice website, nice article of Our World in Data. As of last week, as a matter of fact, the UNECE emission factors are also used now in the electricity maps application that you may already know if you were here at the last Electrification Academy lecture, which is an app where you can see the real-time monitoring of electricity production and consumption. So it's nice to see the product of one's work reused in a real-life application that has probably a better use, direct use, as a report sitting somewhere. Yeah, so maybe I'll just stop here. That's half an hour, and then we can switch to the questions. Thank you. You can also find me on LinkedIn. It's probably easier to contact me.